Recording. Okay. So the session is now being recorded, and let me share my screen. Screen. Okay. So you can see my screen, right? I hope. Okay. So this is the book, and okay. Let me start with the introduction. So have you faced any particular, so before beginning, have you faced any particular problems in solving this problem? I mean, from any understanding problem from the course till now? Any doubts particular from the week one? Anyone?
Sir, like today I started to watch the first lecture in week one, but I couldn't follow it because I studied with the reference material along with me. So just now I asked you what's the reference material.
Okay, okay. So there are a few books that will be covered. But for the week one specifically, it will be Peter Atkins. I think it is mentioned also, right? In the it is already mentioned. You can watch the video and look for if you have any doubts or not. You can always post on the discussion forum. And there is a discussion forum for this particular course, so you can always go there and post your queries. Some of us, maybe me or some other TA, will try to answer your questions. If it is not happening in the live discussion series, you can also post it there. So that is another thing.
Okay,
So
sir.
anyone else had any particular doubts, or else I'll start from the beginning. Okay, so let us see what were taught in the courses. So it was first started with the Rutherford. Can you? Acha, you can't see my screen right now. Let me share again. I'm very sorry. Okay, I think now it is shared. So if you can't see the screen and can't hear the audio, please let me know. I'll stop and I'll try to see what is the problem. So you can see my screen right now, right?
Yes, sir.
Okay. So the first it was taught from the started from the Rutherford model, and where the planetary motion of the electrons around the nucleus was understood, but there was some means problem with this model, which was later solved by the Niels Bohr's model, right? Where it was discussed the concept of stationary state came, and it was also discussed that at individual these stationary states or in this particular orbits, the electron will not emit any electromagnetic radiation during its rotation, so it will be stable. And if it try to jump from a state of energy Ea to Eb, so there will be some photon will be lost, and the energy of the photon will be Ea minus Eb. So then black body radiations was also discussed. I'll not go into deep. I'll just cover these things so that if you had any problems here, if you remember it, then please let me know from these slides. So we'll stop there and we'll try to discuss. Okay. So from there it was understood that atomic spectra is a thing which was not means line spectra is a thing, but which was not coming from the Rutherford model, because Rutherford model you are getting an continuous spectra, which is not true. Actually, you are going to get a linear spectra, because the Bohr's model is more correct version of that, because you are going to get quantized energy, right? That's why you are going to get this line like spectra. And further it was understood that it is not a individual line. These single lines also constitute of multiple lines, which is coming from the Sommerfeld model. That this presentation is over here, so let me go to the another PDF. It is right now here, the module 2. So yes. So there in the from the Bohr models, you will get the expression for the radius and the energy, and the what will be the difference between two energy levels, that will give you the spectral lines. And also you get the experimental value of Rydberg formula. So these things you have already learned. Now the thing was that the from Bohr's model, the problem was that uh, uh, one cannot really, from the Heisenberg model we already knew that the position and this momentum can't be, there are some experimental observable things which can't be measured at the same time. So means there will be some uncertainty in those observables. Like one of such pair is position and momentum. Heisenberg, from Heisenberg uncertainty principle, you know there is uh, a formula that delta x into delta p, that will be I think less than equals to h cut by 2. So that is actually will give you that there will be some uncertainty in, if you measure the positions correctly, then the uncertainty in the measurement of the momentum will be infinite. So you can't really measure both the things at the same time correctly, means accurately. And then I was talking about the extension of the Bohr model, because that Sommerfeld and other later Zeeman, they shown that the what means atomic spectra, we are linear atomic spectra we are seeing, actually it was not linear. When the more suitable or more instrument with good resolution came up, they saw that it is not a linear, that doesn't contain only one spectra, that linear spectra of the atoms. So it is a multiple of. So why it is like that? Because there are some the spectral fine structures are coming from the azimuthal quantum number, that is L, and your primary quantum number was N. So right now I should not say the quantum numbers, because till now we are still in the classical field. So quantum or the wave mechanics is yet not discussed. So when it will be discussed, you will see that this classical theory will have its quantum or wave mechanical counterpart in the quantum mechanics. So these are already, you know that in presence of magnets, or in presence of some other effects, so your atomic spectra is going to split, and you are going to get spectral fine structures. So your N gives you energy. L, the azimuthal quantum number, will give you the spatial orient will give you the spectral fine structure, and the Zeeman effect is coming from the magnetic quantum number, that will give you the spatial orientation of the angular momentum. So that's all being taught, and then I discussed this thing earlier, the uncertainty principle, and then from the, now there comes the uh, uh, dual wave particle duality, right? So earlier different experiments were being done by Stan Garlock and G.P. Thompson, that that photon or the light is a have a wave nature. But from the experiments of from the experiment of Einstein, the photoelectric effect, you come to know that it also have a particle nature. So D. Broglie actually discuss about this, and from his means equations, or from his actually his work, you are coming, you get to know the wave particle duality, and what will be the wave number or associated with the what will be the wave number associated with the matter, even a matter like electron. So this was the thing I was talking about, the G.P. Thompson experiment and Stan Garlock experiment. Then later from the de Broglie hypothesis, it was what will be the wavelength of this suppose a matter or a matter wave in some electron something, we can calculate. So why can't we really? Can anyone tell me why can't can't we see the wave nature of a human or a car or a in general a macroscopic object? Why can't we see the wavelength, or can anyone have any guess? Means from for electron we can discuss, right, that it has some electron moving at a speed of 10 to the power 6 meter per second, that will have a wavelength of 7 to 10 to the minus 10 meter, which is actually angstrom, right? 7 angstrom. So why does a macroscopic element like a human or a car uh, moving at might be the same speed? Let us say that the car is moving at a speed of 10 to the 6 meter per second, which is means in reality it is not true, but mathematically if one consider a car is moving at a speed of 10 to the 6 meter per second, then can anyone guess what will be the wavelength? Can you really see the wave nature of car? Anyone in the mm, discussion forum? Can anyone answer? Is my question clear? Hello, am I audible? Yes, because of the mass, Priyanka. Yes, yes. Navid, you are correct. Wavelength will be too small, so that is why there will be no such. So these diffraction experiment for or the wave nature of this. Yes, so this wave nature is actually being seen by the diffraction patterns, right? But the diffraction pattern will come where you get something slit with or some nickel crystal or some crystals or some slit of that particular resolution or of that particular lambda that can diffract that wavelength. But the for a macroscopic object, most of you have given the correct answer. Priyanka, Nivid, and another one was there. So for a macroscopic element, the lambda will be too small. Why? Because this mass is too high, right? Even if go for with the same velocity, mass will be too high. That is why your lambda will be too less. And that is why what you are going to see, your lambda is too small, so you don't have such thing that can diffract that wavelength, and you can't see the wave nature of that macroscopic object. Even in the case of helium atom scattering, it was observed, but the calculated de Broglie wavelength for helium was found to be 42.5 into 10 to the power minus 12 meter. So this was also too small. So suppose a human or for an atom we can't really see, but for electron the mass is too less. That's why we are able to see the wave nature of this. So so these are the things that was discussed in the class, and then it comes that if matter have both particle and wave nature, particle, so can't we really get a means what is the wave nature looks like? So then come the Schrodinger equation and other things where the wave mechanics come into the play, right? So from there I think these are already discussed. So so anyone had any doubt in this Schrodinger equation part particularly? So this is the time dependent Schrodinger equation, where which is I h cut d by dt of the psi. This is the capital psi which has, and x and t means the space and time dependency, which is equals to the Hamiltonian, which is the operator, and operating on the same capital psi, which is uh, again a function of time and space. So and this Hamiltonian is given by this minus h cut square by 2m del square plus its potential energy. So this part I can you see my cursor? Actually, can you see my cursor? I don't think so, right? No, you will be able to see because I have shared my screen. Um, so can anyone respond if you can see my but the Planck constant is the main constant. Uh, uh, Mr. or Miss Pandey, so what is your full name? So I could means. Um, so you are saying this thing about that h by means the moment for the wavelength question, right? So h is already, yeah, h Planck constant is the main constant because h has a 6.626 into 10 to the minus 34. But what I was saying that everything else is same. You keep the velocity also same, but you are changing the mass of your object. From a macroscopic object, the mass is high, right? So the change is in the mass. So so the mass will be high, so that's why your lambda will be even bit small. And obviously Planck constant is the main constant because 6.626 into 10 to the power minus 34 joule second, that is the main thing, that is the smallest thing is there in the equation. So let me come back to this. So what I was discussing that about the Schrodinger equation, this is the general form, this is the time dependent form, which has a space and the time dependency. By separating the variables or the you can what you can get that individually you can get a time independent Schrodinger equation, which is actually not a real thing, means it is a consequences of time dependent Schrodinger equation. So, Schrodinger actually gives the formula for the time dependent part. So from there it is arrived that time independent thing. So how that thing was coming to the time independent Schrodinger part, that you can see from the videos by separating the variables like x and t, space and time. One can do that easily. Very nominal mathematics is required for that. Please watch the videos. I guess most of the things will be clear. So this separation of variables, I can tell you, this is going to be a very big thing in the or the very big theme of the upcoming lectures also, where you need to solve the Schrodinger equation for a little complex systems like 1D box, 2D box, 3D box, or maybe hydrogen atom, where this separation of variables is going to play a crucial role to get the for solving the psi of x. But I think in the week 2 or in the after this I will discuss the postulate of this quantum mechanics. A few of the postulates. The postulates means these are already there, so means there is no proof for this, but there is some physical significance of this. Means these are like Newton's laws of motion. I think Professor Datta already discussed these things in the lectures. So I'll just quickly go through the postulates so that we can have our discussion on the numerical problems, and we can do the assignments. Okay, so the first postulate is that psi n, this capital psi, is the state function. Okay, so these have the all the information of that uh, matter or particle, whatever you are looking at. Okay, so you need to give it a appropriate operator. You have to use an appropriate operator to get the appropriate or your whatever you want to know from this wave function. So this psi n is known as a state function or a wave function, which have a complete information of the system. Okay, so you will operate some operators on that to get some eigenvalue. Okay, so this is known as eigenvalue equation, where your operator is a, which is operating on your psi, and you are getting an eigenvalue of an. Okay, so this will give you the measurement or something like that. That will we will come in the next PDF. Okay, next file. Let me open that. I know I'm going a little fast, but please stop me if you have any question. I can't really see the chat box from here, so please unmute yourself and ask the question. I'll go back to the chat once if you have any questions. Okay, so I'll again go back to the PDF. Here I can't see your messages. Please ping me. You can unmute yourself and ask the question. Okay. So now this is again the same thing. The separation of variables was shown in a nice way. Here I hope you got the gist what I was trying to say. Here was the let me zoom out a little bit so that you can see. So this was the first postulate what I discussed, that psi n is a wave function of the state function, which have the complete information of the system, which from which you will get the information. Now second thing is that there are, so this is also known as the eigenvalue equation, where why eigen in German means single valued. So you are going to get, if you are operating on this eigen function, you are going to get a eigenvalue, right, a single value for that. If you change your psi n, then you are going to get a different eigenvalue. So this n is right now, think of this as a notation. Later it might change. Okay, So these are the things. And for quantum mechanics, I think Sarah has written one thing. Yes, the quantum mechanical operator. So for each means classical uh, observables, there is a quantum mechanical operator. Suppose you want to get the energy of the system, the total energy, then you already know Hamiltonian is your operator. You want to calculate the kinetic energy, then you have some operator for that. You want to get the potential energy, for that there is some, or the position or the momentum. For each of these classical observables, uh, you have some quantum mechanical operators in operating in the quantum mechanics. And for each of these observables, your eigenvalue is going to be real. So this is very important, because your these quantum mechanical operators are actually Hermitian and linear. So these two terms are very important, which will come back in, I think it is taught in the, I think week 2 or week 3, I guess. The Hermitian operators and these things will be taught again in details. So don't worry. I think there is a separate video for that, or I will come it to next week. What is a Hermitian operator and what are the other means consequences of a Hermitian operator. But till then, you just remember or understand that all the quantum mechanical observables, or the physical observables in the quantum mechanical operators are actually Hermitian and linear. So let me write something, and I think you will get the thing what I'm trying to say. Can I write here? Okay, I can't write here. I will able to write here. Okay, I'll write something here. So what I was talking about, linearity, linear operator. So your, suppose you have a operator something a, okay, a plus b, which is actually your operator, suppose is c, which is actually a plus b. So if you operate on some function f of x, so it is actually your a plus b is operating on f of x. Okay, so this is actually your a f of x plus b operating on your eigenfunction. So f of x is your eigenfunction. So not a eigenfunction here, but a function here. So what I was trying to say, this plus and minus, or suppose even derivation. So these are linear operators, but root is not a linear operator. Okay, square is not a linear operator. So suppose you are squaring this thing, right? A plus b, this square. So it is not equals to a square plus b square, right? So it is equals to a square plus b square. Actually, for operators, it is ab plus ba. Okay, it is not 2ab. So you will come to know if it is at all a different thing, ab or ba are at all different or something, that will come into the later picture. But you get the idea, the squaring is not linear. So 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 it is not a linear operator or a square root. Okay, but derivative or even double derivative, these are linear operators. Plus minus, these are linear operators. Another thing I have discussed, that is Hermitian. Hermitian operator. So can anyone tell me what is the definition of a Hermitian operator, if anyone knows from earlier knowledge? Hermitian operator, anyone in the meeting? Please unmute yourself and please join in the discussion. What will be the means definition of a Hermitian operator? Is anyone typing? Let me check if anyone is typing in the chat. Not yet. No, that is Hamiltonian. Total energy of the system is Hamiltonian. So that is not Hermitian. Hermitian is a type of operator, and the not type it's a type of operator. Let me give you, let me write here something so you will understand. So the total energy, so the thing you said, that is Hamiltonian, it is not Hermitian. So this is Hamiltonian, which is actually your total energy, operator for total energy, which is actually your, this is kinetic energy and this is potential energy, right? So the kinetic energy is again minus h cut square by 2m del square, and this is your potential energy. So this is whole together is Hamiltonian, but so this is the example of an operator, and Hermitian is a type of operator. So what I said, that your all quantum mechanical operators are linear and Hermitian. Okay, sorry for this upward curvature in the writing. So I am using a writing board after a long time, so that is why it's happening. So I already told you the definition of a linear operator, right? And the examples, what could be the linear operators. And Hermitian operator, the definition is actually, suppose A is your Hermitian operator, it is operating on a wave function psi, and there is another wave function, and we need to take a complex conjugate of this. So what I am going to give you is a mathematical description of a Hermitian operator. And so what you are going to do, you are taking A is your Hermitian operator operating on a wave function, and there is another wave function whose complex conjugate you are multiplying at the left hand, and you are doing an integration all over the space. This d tau is known as the volume element, right? This is, I think, already taught in the that Born interpretation of the wave function, right? I think it was already discussed. Volume element. So, so for a Hermitian operator, if A is a Hermitian operator, then what you are going to see, that is, you are going to get psi star A phi d tau and integration of this, and then you are going to get a complex conjugate of the whole integral. Okay, so this is a mathematical definition of a Hermitian operator. So A is a Hermitian operator, then only you are going to get this LHS is equal to RHS. So when someone will ask you to prove that some operator is Hermitian or not, you have to show using having to means you have to take this complex conjugate of the whole thing and show that is the, it is coming as the same thing. The operator is not changing. Then it will be a Hermitian operator. And all the quantum mechanical operators like energy, then your position or momentum, whatever is physically possible, those are all Hermitian operators and linear. And one more thing, these one of the consequences of this is, of a Hermitian operator, that eigenvalue of this Hermitian operator is A, currently I am denoting A, will always be real. Have you seen energy to be imaginary or position imaginary? No, right? So that is another point. So most of the cases, if someone asked that what is a Hermitian operator, the definition should not be that it's whose eigen values are real, but you have to give this mathematical definition, and these are consequences. Okay, this is not a definition that eigenvalue will be real. This is the consequences. Okay, so these I think will cover deeply in the, I think, next few weeks. Till then, let me come back to the postulates. Is there any question in the chat box? No. So let us again start with the postulates. So another postulate was given that all the eigenfunction of the quantum mechanical operator are orthogonal. So I am not going deep into this. I hope you got the point. Here from here also what are orthogonal thing, and so from here what sir was talking, that these each states, these each states are individual stationary states. Okay, so but the n is different. You got my point, right? So or you can say these are all stationary states, but this is psi, if this is psi, this is phi. You can think like that also. So when you point by point you multiply and then integrated all over the space, you are going to get 0. Okay, but when you are going to integrate on the same state, you are going to get 1. So that is the normalization and thing, and this is the orthogonality thing. I hope you are getting my point. I will come back to it again because we will solve some, I think, numerical problems on that. And then the measurement theory is going to come, and there I think you have already taught that there are three views: one realist view, one orthodox, and one agnostic. But quantum mechanically it has been shown that the orthodox view is true, which is actually before the measurement your state is entangled, and when you do the measurement, you what you are going to get the value that is, and you can say collapse of a state, means it will collapse to a particular state and give a eigenvalue of that state. So I will discuss this measurement and the entanglement thing theory in a numerical problem next week, because I think there is some numerical problem in the assignment which will require this understanding. So and as the assignment is due till now, so I can't really discuss the assignment, because as we have been taught or told by the NPTEL staffs that after one submit the assignment, then only you can discuss the questions of the assignments. So we'll do that later. So we'll have some numerical problems on this entanglement thing or the collapsing of a wave function. So don't worry about that. We'll discuss that in the next. I have some numerical problems for that. So the thing is that we are going to deal with the orthodox theory, but it will come later. But and let me go to the another PDF, the last one. Okay, so here the thing is that we'll talk about the Born interpretation of the wave function. You have already know that your state is completely, so this is your first quantum mechanical postulate, right? That psi is a it has the complete means information about the system, and you can get all possible information from psi of t by using uh, different operators. Now the thing is that the probability, what is probability of the system, means finding on particle at a particular position. So that you got the idea that the probability will be the square of modulus of this psi of your wave function multiply by n. Here it is not a volume element, here it is some dx distance for a one dimensional case, and for a 3 dimension you are going to get a volume element. Volume element, this d tau is nothing but dx dy dz. Okay, so that is nothing but so volume element is a very small unit uh, area, a volume, right? So when and that is why your this psi xt square, that is probability density. So you are multiplying probability density with the volume element to get the probability. So more often than not we get the mistake that psi square is the probability. That is not the thing. Psi square d tau is the probability. Okay, we will solve some numerical problem on that, don't we? So then another postulate. So let me check if you had posted any questions or not. No, not yet. Please, if you have any problem, please unmute in between and please ask question. Okay, because I don't know which part you will particularly have some difficulties to understand. It's not like that I can give the answer right away. I may also not get the whole idea, but we'll discuss it anyway. Okay. Okay, so the next theory is that we were talking about this, right? The measurement thing. So the one of the postulate is that the average value of the observable of corresponding to the operator A is that is given by this bracket notation. I should not say bracket notation here. So inside this thing A, so that will be your psi star A psi. Okay, so but the thing is that here they have already assumed that psi is normalized. If psi was not normalized, then let me write you the form what it should have been. Okay, so what I was trying to say, so if you want to get a expectation value for this operator, so that will be, so this is known as expected expectation or expected value or average value, the same thing known as many things, right? Average value. What I was trying to say, suppose you are so we are talking about the measurements, right? Suppose you are doing a measurements multiple time. Okay, so you have done a total n number of n number of measurements, and from there, after each measurement, suppose you got n1 times the value you got a1, n2 times you got the value a2, okay, n3 times you got the value a3. Suppose you have done infinite number of measurements, okay, and this is the value you got. Okay, so how do you calculate the average thing in classical thing? So the average, you will say that the average will be n1 a1 plus n2 a2, right, like this, n infinity a infinity this many times, and by the total number of measurements, which is nothing but n1 plus n2, like this, right? So by classically you will get from this, but in quantum mechanical problems you will get this very easily by using this postulate, which is integration again, or integration of your psi star, your wave function, then the operator you are using, then psi, and then your volume element. What does this mean? This means that you are operating your operator on your psi and multiplying with a complex conjugate of your wave function and integrating or summing all over the state. So this is the thing that was given in the presentation or the PDF file, but you should also know if psi is not normalized, then you have to write like this, psi d tau. Why it was not written actually? Because sir was coming to the normalization thing after this. That is why I think yes. So the normalization of the wave function was discussed later. Means from now on. So this is another means you can say another postulate. Means there are, if you go by the books, there are 4 postulates. So what Professor Datta has done, that he broke down the postulates into means multiple postulates, so that you have a better idea of that. So you already know this psi star psi d tau is the probability, right? Now the total probability should be 1, because it should not be 0 at total or some other value. It should be unity 1. So that is why your normalization thing is that all space, integral over all space, psi star psi d tau should be 1. and this is no, so this is the integration common notation you have already shown, and this notation is known as the bracket notation. Okay, so the first part is known as bra and this part is known as skate, so this is known as bracket notation. Okay. Now, so comes the thing of the acceptable wave functions. Can anyone tell me, means as you have already gone through the lecture, that's why I am asking, uh, what is the, means what are the points of a acceptable wave function? So you guys can tell me, and please unmute one of you maybe and say, I'll write here that conditions of conditions of uh, of an acceptable wave function, when a wave function is acceptable and when it is not. Please someone volunteer. Anyone? If you are writing on the chat box, please write. That will also work. Yeah, someone unmuted him also. Yes, single finite. Someone has written. You can also check the chat box. Satya Manikanta has written single finite and continuous wave function. Continuous is the main thing, and single valuedness is another thing, and it should be finite. Okay, and anything else regarding the uh, first order derivative or something like that? First derivative exists, but you are going to actually see this first derivative existence is not really first derivative existence is not the point. I think the first derivative is also an eigenfunction of your operator, I think something like that, right? Am I making sense? So that point is actually not going to be true in all the cases. So I'll come back to that. But continuous, single valuedness, and finite is the main thing. So let me come back to the here um, the examples. So the first one we can see what is it at infinity. You can see this is finite, right? And this has, for individual x it is single valued and it is also continuous, right, in this boundary. So this is an acceptable wave function. And then the next one, right, this is something like a exponential decay function, right? So it is also an acceptable wave function, because you can see at infinity it is going to be almost zero, right? And it has some finite value. And what about this thing? This is also known as sin x by x actually, right? This function is known as by sin x by x. If it only had the positive lobes, then it was sin square x by x square. So these are the question may come in the assignment or in the exams, that if a sin x by x is continuous or not, something like that. We'll definitely discuss those kind of numerical problems. Okay, so as you can see, this is an acceptable wave function because at infinity or at boundary this is finite. So one of the main term for this is square integrable. Okay, first is obviously single valuedness, single valued. Second is continuous, and this finite or normalizable, one can write it or normalized. It can be always said like square integrable. What does I mean by that? Square integrable. That means, so your this is your psi star psi d tau, right? This is your square of the wave function and integrated all over the space, all space. should have some finite value. It must not be 1, then it is normalized. But suppose you are given one wave function which is not normalized, but it is acceptable, right? So you can calculate the normalization constant yourself, and we'll actually do and I am saying in all the cases that we'll do some numerical problems obviously, but actually I think those problems are coming in the next week, because week 1 assignment will discuss in the next week. But one can calculate the normalization constant as well, what I am trying to say. So if it is not normalized, then also it is acceptable, but it should be square integrable, means the square of the wave function. See, this psi star is required, the complex conjugate, but if psi is real, okay, then you can write it as psi square, right? But if psi is imaginary, then you should write psi star psi. So instead of this, you should write this. Sorry, not instead of this, means in place of this, you should write this. And when psi is right, you can take the psi square. Okay. Okay. Let us see what else is there in the lecture. So there are some means example of non-acceptable or unacceptable wave functions. Why it is not why it is unacceptable? Because it has discontinuity 1, and second is it is not single value, right? At this position it has 2 values, one thing. So it is said that it is unacceptable because it has a different slope. So what is dψ by dq? So that is the slope at this point, right? So that is, the slope is different at this point, that is why it is said that so the a is the first derivative should be continuous. I think someone wrote first derivative is should exist, and I said first derivative should be an eigenfunction, which is not true. The first derivative should be continuous. But the thing is, this will not hold always the truth, because you are going to see the first uh, problem we are going to or the first system we are going to check, that is a 1D box. There this uh, restriction doesn't really work, that dψ by dq. So we'll discuss that more in that class. What about this kind of wave function? It is not acceptable because this is not single valued, right? At this position of x there are 3 values. So that means the probability of finding at this particular points there are 3 probabilities, which can't be true. Okay. Now one thing I missed, that this psi square, this probability of finding one particle in all the space or the wherever the boundary condition is there, it should be in between 0 to 1, right? The total probability is 1, but the psi square or the probability can be less than 1 also, and but it should be more than 0. So it will be in between 0 to 1. Okay, another thing, that this is unacceptable because it is going to infinity at x, right? And it is, I think, also not continuous, you can also say that. Okay. So these are the restriction that we talked about. And then we are going to solve some exactly solvable systems in the upcoming week. So one of such is free particle, another will be particle in square well potential, example of which is 1D box or 3D box, and then obviously we are going to discuss hydrogen atom. Okay, and these are some exactly solvable systems. Even more systems are going to be studied in this lecture, like your what is that thing is called, rigid rotor, and many electron atoms that are going to be studied. Okay. So I am not discussing this free particle thing because it will be discussed, I think, again in the second week or something like that. So let us go back to the chat box, see if Yeah, Satya has written that it should be continuous even after first derivation. Yes, that is what mean by the first derivation is continuous. But I am repeating myself again. But this restriction is not going to hold true. Actually, this has been told like this that the first derivation will be continuous, but this is not really true. So that will come back. But so till now, do you have any general query about the course material that was taught in this particular week? I just quickly gave you a quick summary what Professor Datta has taught in the five lecture videos. If you have any particular query, you can tell me. Anyone? No? Okay. So we are going to solve the first week, or the not the first week but the 0th week assignment. So but in this case I will not give you the answers. Means I will try to help you solve it, but you have to means be uh, in the discussion. Means you have to solve it, and someone has to voluntarily unmute them and um, say the answer or how to solve it. And so we don't want you to solve it here. You can solve it later also, but give me the idea how to solve this. Now, the first question is, what is the frequency of light having a wavelength of 4.50 into 10 to the power minus 6 centimeter? Before this, let me tell you, this is a physical chemistry course. The main thing of, obviously will be the solving the numerical problems, obviously understanding and then numerical problems. In case of the numerical problems of physical chemistry problems, one should always look at the units or the dimensions. Okay. Suppose, what is the unit of Planck constant? We know the value 6.626 in 10 to the power minus 34. Can anyone tell me what is the unit?
Jules.
Joule second. Exactly. One should not write it joule per second or something like that. And one should also know that what is the means relationship between each units or each dimensions. So that will help you to solve the problems better. Okay. Or else one will means in many of these quantum mechanical case you are going to get the mass value as AMU in it. Okay, it will be given in the question, but when you are going to solve that particular question, most of the time you have to go to gram, right? Gram or kg, this kind of unit. So you have to have the idea that how to convert AMU to kg or AMU to gram. Okay, so these are the things you please keep in mind. This in this course this is going to be very important. You have to check the unit always, and you have to know that what is the conversion means conversation value from AMU to gram, from joule to electron volt, or electron volt to joule, vice versa. Okay. Okay. So this is fairly easy. What is the frequency of light having a wavelength? Wavelength is, so this is coming from the your. So you don't have to mark up what is wave lambda is equal to what. So you all, so these we all know, right? Hc by lambda. So what is given, and this is also h nu. So what we are going to get, h cut. So lambda is c by nu, right? Or nu is c by lambda. Nu is c by lambda. Yeah. So we are getting it from here only. So that's how you will get the frequency. And from centimeter, what you can do, you should always go to the SI unit. From centimeter go to meter. Okay, and then solve this. Then, or if you taking the centimeter unit as wavelength, then you have to take it as a 3 into 10 to the power 8 centimeter second inverse. Okay, that one can also do minus 6 centimeter. Centimeter card, second inverse is your unit of the frequency. So that one can calculate and see what is the value coming as. At least we can get the order. So that will be 1 by 1.5 into 10 to the power 14 or 1 by 10 by 15 into 10 to the power 15. In this order you are going to get the answer. We can also see what is there in this similar unit. So this is not the correct answer. We can see this is also not. This might be one possibility. This might be one possibility. This will not be a possibility from the order we are seeing, right? So you can see if it is 10 to the power 15, then it is less than 1. Am I talking sense? Please correct me if I am making any mistake. Yeah, I had 10 to the power 14, right?
Option E is the answer.
Option A is the answer.
E.
Yeah, correct. In between two are the correct answer. Yes, E will be the correct answer because this will be 100 by 15 and this will be 10 to the power 15, right? Yes, correct. Next is Heisenberg principle state that so we all know that which one is the correct answer, but can anyone say individually that what this, from where we get this idea that no two electrons can have the same, no two electrons in the same atom can have the same set of 4 quantum numbers, which
Pauli's expression.
Pauli's exclusion principle, correct. So then two atoms of the same elements must have the same number of protons. Is this isotope? So this is some, I don't think this is some rule, right? Okay, what is the next thing? It is impossible to determine accurately both the position and momentum of an electron simultaneously. That's what is the Heisenberg principle. Here one thing I was saying earlier that for a pair of operators, particular operators like x is position and px is the momentum along the x-axis. Um, so this particular pair has this uncertainty. Then your energy and time will have some uncertainty. Not all the operators are going to behave like this. Something because these are not commutators or something like that. Do you have any idea what is a commutator? Relationship between operators. And one mistake I am also making, you please don't make that for each operator please give it a hat. So this is a common notation. So if you miss that somewhere, you may means miss out some you may face some problem in solving. So you should always remember. So what I was talking, this is a commutator relationship. It will be, if it is equals to 0, I guess, so then it is called a commutator relationship between these two operators. This is actually nothing but x p. This is not actually 0, means for this particular pair these are not, they don't have commutator relationship. That's why actually there is a uncertainty in the measurement between these two delta px, which is I think less than by h cut by 2. Less than or greater than? Uncertainty, yeah, I hope less than equals to. And this is what I was trying to say. Px. So this is what this uh, bracket means, the third bracket. Okay. So this is not 0. So that is why you will see that they will see. And those operators which commute, there you won't find the there you won't find the uh, uncertainty thing. Okay. No, one common means just give you an information. Please check that from the book. Okay, I think that was not discussed in the lectures. Okay, now what? So this is the correct answer, but still let us go by the things. Electrons of an atoms in the ground state enter energetically equivalent states of orbital singly before they pair up in any orbital of the set. So do you remember which principle is this? Hund's rule, right? I don't know if I am making the correct name, Hund's rule, right? That it will enter uh, uh, means of in a, of singly means, so these are the things, right? See, for a p orbital we do like this one, so p3 we will do like this. We will not. So this is the correct notation for a p3. This is not, right. So I guess this was Hund's rule. And another is charged atoms must generate an magnetic field when they are in motion. I think this is coming from Maxwell's principle, something like that. So but the for this question, Heisenberg principle, this third one is the correct thing. Okay, so let us go to the next question. Which atomic orbital is spherical in shape? Can anyone tell me out of these things which is spherical in shape?
Yes.
2s. What will be the shape of a p orbital?
P think it's
Dumbbell like, right?
yes, yes.
Yes. I'm not going to 3D and 4F. Uh, you can draw it, but in 3D it will be tough to visualize. But in this case, I think Sir has shown those plots, and obviously you can get them in the quantum physics or chemistry books. So not all of them are spherical, only 2s. And the next question is, the radiation and the matter have properties of both the particles and wave, that is called the wave particle duality, we know that. And then the Max Planck's great discovery was the radiation energy is emitted in packet, we know, that is known as quanta, right?
Yes, yes.
Yes. And each quanta or each photon, not each quanta has a few photon, it may have photon. What is the energy of a photon? That is E is equal to hc by lambda, or h nu, where nu is the frequency, h is the Planck constant, and the other things. So from here actually most of the questions come, hc nu bar. Nu bar becomes wave number. So these are the very general means equations from where the question will come. Okay, you just need to know that what are the relationships. So question 6, the thing we learned in the week 1, that acceptable thing. So can anyone tell me which of these 4 is an acceptable wave function and why, and which is not a acceptable wave function and why? This we have discussed, right? Sin x by x. So this will look like something like, suppose, sorry, so this is an x-axis, suppose, okay, and then your f of x is this. Sorry for the bad drawing, please bear with me. Amplitude will actually increase. Very bad drawing. This is symmetrical, okay, and it will actually eventually at infinity it will be gone. It will be 0. Okay, so this is how a sin x by x really look like. So it is always better, whenever you are given a function, to try to plot it. Okay, you first try to come from the plus x and then minus x, or put some values of x, try to see what is the uh, plot looks like. Okay, from there you can understand that if it is acceptable or not. Like, I got this thing, right? So how did I got this? Let me tell you that I knew this, but one can multiply 1 by, what does 1 by x looks like, and what does sin x looks like. Sin x, you know, it looks like it has a wave nature, right? And 1 by x, I really So it will have a dumping kind of, you can say, uh, uh, so 1 by x will look like this. But the thing is, one may say that for x is equal to 0, what will be the value of sine x by x? Oh, I got gave you. So this is will come, sine 0 will be 0, this will be 0. So it will be it will not be defined, right? But here you can take a limit. What does a limit, taking a limit means? Sine x by x will be, so you know the L'Hopital rule, right? In most of the cases it is mispronounced as L hospital. Especially I read it like that. Later I know it is L'Hopital rule. So you can take a limit of this, you will get cos x, means derivation of the numerator and the denominator. So then you put the value of x, that is cos 0, that is 1, right? So actually this sin x by x is actually 1. Limit extends to 0. What this means, that at this point x is equal to 0, there is a discontinuity, but just before 0 and just after 0 the value is 1, means it is converging at that point. So it is a removable discontinuity. By taking the limit you can see that the value will be 1, that's why it is a continuous. So the that one condition is fulfilled, then it is single valued, right? So that condition also fulfilled. Then if you check the um, what else is there, the square integrable, right? Don't think about that first derivation is continuous. Don't have, you don't have to think about that in this point of time. Think about the rest of the another one, that is square integrable. So as you can see, at plus infinity, at minus infinity it is 0. So this is a finite wave function, right? So actually this will be a acceptable wave function. Please check for B, C and D. So you don't have to, means just for this assignment I'm telling you, you can go to any online graphing website. It is best to plot yourself, but if you want to know quickly, if it is not, check the wave function, how does the plot look like for this in any graphing calculator or something like that. You graph it yourself. I can graph x sin x and e to the power a x square, this I can graph, but to be honest, when I first saw sine inverse x, I also panicked. So I went to some graphing calculator and saw that, because that range and those things I forgot that for the trigonometric function. This is actually the sine inverse, plot of sine inverse x is not means easy one. Sine x is easy. Can anyone tell me here that what will be the plot of sine inverse x? Here, anyone present want to plot it right now?
Sir, I don't know how to do the plotting. Can you just help with that?
Okay, so see, I'll give you the easiest example right now for the B. Okay, so B is sin x, you know, one of the part is sin x, another is x. How does x varies? So how does x varies here? X will vary as, suppose something like this, right? If this is your f of x, means your f of x is x, so at 0 it will be 0, at 1 it will be 1, 2 it will be 2, something like that. You get the curve of this, right, for x. For sin x you know this. So what you can do, that at individual point you can multiply and check how does x sin x looks like. Similarly for sin x by x you can do that. Another thing, what means that you can check yourself also. So see, let us see how does f of x sin x look like. Okay, So at x is equal to 0, what is the value? 0, right? Then x is equal to pi by 2 into sine pi by 2, which is 1, right? Then x is equal to pi by 4, means the in between point. What is that? Sine is equal to pi by 4. This is pi by 4, and sine x is sine pi by 4 is 1 by root 2, I guess, right? So you can get these values and plot yourself. And another idea was something like let me remember how does. So I got a mistake here. The sine x should go through this point, right? X is equal to 0. So this is just an error in drawing. So you can get these values for different x. You can get the values of f of x and then plot it. Okay. For most of the cases, uh, so you are multiplying, right, here. So suppose 0 into 0, you know the value. For pi by 2, for x is equal to pi by 4, pi by 2, but like this you can graph it. Let me check. X is equal to 3 pi by 4, it will look like uh, 3 pi by y will be 3 pi by 4 into sine 3 pi by 4, which is I think equivalent to 1 which will be 1 by root 2, I guess, because at second coordinate sine is positive, right? It is pi by 2 plus pi by 4. Then x is equal to pi, it will be y will be pi into sine pi, which will be 0, right? So how does it started? X is equal to 0, then x is equal to pi by 4, which is here. What is the value? The value is pi by 4. I don't really know the value, means from here I can't really do it, but you can plot yourself, right, in any plotting graph or something like that. Will you be able to do that if you get the values like this?
Yes, sir. Yes, sir.
You
Got
can
it.
try. You can
Yes,
try
sir.
this approach,
Yes.
and I will tell you another approach. I just can't remember it. I will give you another approach. So you can directly from here. You can also see what will be the values. Okay, it will follow some kind of x sin x. You can will be able to will able to do that. So next day at the beginning we'll solve this question. Okay, how to plot this and the sine inverse x and the other things. Okay, to get a fair idea. And another thing is a cheat thing. What I am going to tell you, you can always go to graphing website. Online is there. You can put the function and check the wave function. But first try to draw the graph by yourself. If for sine inverse x I went to graphing website because I could not do that. I will be honest with you. But for x sin x, you don't have to go to the plotting website. Please try to do it yourself and you'll get the idea. Sin x by x is a very common physical chemistry thing, will come in different portion. So that's why I knew how it looks like. Okay, but I'll tomorrow or the day after tomorrow, sorry, the next class I will discuss this thing, how to plot this curve. Okay. Okay, so let us go to the question number 7. Here comes from question 7 to question 10. We'll discuss one by one. Okay, so today we will not discuss this question because 1D box or 2D. Now the next question about the hybridization. This is yet not taught. So can anyone from their earlier knowledge can tell me that what will be the wave function of a particle in a box? What will be the properties? Means which properties are true for that from your earlier knowledge, if you have studied quantum chemistry earlier? Anyone? The wave functions of a particle in a box. Can anyone tell me if wave function can be imaginary or not? Can wave functions be imaginary? Anyone? Actually, it can be imaginary. You will see that in hydrogen atom problem, most commonly found your that phi part. So that is imaginary. E to the power my im phi. Okay. So your wave functions can be imaginary, real and imaginary, but your eigenvalue for a quantum mechanical operator will always be real. So you are going to see that in a few upcoming classes that wave functions of a particle in a box will be real, and I told you that first derivative will not be continuous for a particle in a box. So this will not, these two are not going to be correct. We will discuss that in detail in the next few classes. But the wave function will be real for a particle in a box. It will look something like the psi of x will look something like 2 by n sine n pi x by l. Okay, where n is your that quantum number or which state it belongs to. So which stationary state n can be, n will start from, n will not start from 0 here, n will start from 1. So you will see why it is something like that. Okay, if n is 0, then you see that psi of x is 0, right? Means you are saying that your particle is there, means the wave function will be 0. That can't be true. Okay, for every x your particle, means you are saying that your particle got, or the system got annihilated psi of, if psi of x is equal to 0. So actually these quantum numbers will be starting from 1 to something. I am digressing, I'm sorry, but you will get an idea of these things. And the fourth option will also be true, that have greater number of nodes as n increases. We'll discuss this thing. uh, this will be taught in hydrogen atom problem. Admit means after hydrogen atom. Okay, when we discuss the bonding, hybridization, those things. For now, let me give you an idea. You all know what sp3 hybridization means, but the thing is that which one of this is true, that s orbital is 25% contribution, right? That is true. And is it true that each of px, py and pz orbital is necessarily 25%? This is not true, but the total p combined will be 75%. That is true. Pz orbital may be 0%. That is also true. Okay, but it is not true that px, py, pz will individually be 25%. So again we'll come back to this. Um, I should not discuss these things here right now, because anyway we will discuss it later. So let us solve some numerical problems I have from Atkins book. Okay, or I should not say solve, but what should I say? Here is the Peter Atkins book exercise. Can you see the my screen here and the
Yes, yes.
exercise problems? Yes. So what I will try to do, I will just zoom it a little bigger so you can see it better. And whenever we are doing some question, is it highlightable? No. So okay, we'll try to discuss this whole exercise as soon as possible, because we'll end by 8 or 8:10 maybe, if time permits. We'll try to solve the numerical problems or discuss the numerical problems. You can always go back and try to solve it yourself, right? We'll discuss it, the what can be the formula we can use or something like that. But for this, I need active participation from you. Okay. And you guys are participating, I'm happy. Thank you. So let's start. So the first question is, to what speed must an electron be accelerated for it to have a wavelength of 3 centimeter? So let us first understand the question. So the question says there is an electron, we need to get the velocity, and the wavelength is given 3 centimeter. Okay, so what are the things given? Lambda is given, and the problem is given that is an electron. So we know the mass of the electron, right? What is the mass of electron? 9.11 into 10 to the power minus 31 kg, right? This is known. So m is known, mass is known, lambda is known. So we want to calculate the velocity or the speed. So what is the thing coming to your mind? Which equation can we use? Anyone? Which equation can you use? So we have the what are the things we have? We have lambda, we have m. We yes, anyone?
De Broglie wave equation.
Correct. De Broglie wave equation, which is uh,
Lambda equal to h by p.
yes, lambda equals to h by p. Lambda equals to h by p, or one can say h by mv. So from here we got the lambda. We know h, right? H is 6.626 into 10 to the power minus 34 joule second. Lambda you have 3 centimeter, right? Better to convert it into meter, right? 0.03 meter, right? And you have the mass of an electron, you have mass of E, that is 9.11 into 10 to the power minus 31 kg. Okay, from here you can get the velocity, right? P will be h by lambda, m lambda. This is fairly easy. So what you have to understand, that you have to get what is given and which equation you have to put. Okay, that is very easy. So you will be able to solve the second question also, right? To what speed a proton be accelerated? So electron become proton, so mass will change. So you check the mass of an proton and do the same thing, you will get the speed. So that's easy. Now the second question, the fine structure constant alpha plays a special role in the structure of matter. Its approximate value is 1 by 137. What is the wavelength of an electron traveling at a speed at alpha c, where c is the speed of light? Note that the circumference of the fast Bohr orbit in the hydrogen atom is 331 picometer. So there are lot of information is given in this question, but from the previous question, the same thing, the speed of light is given, or the speed of electron is given, sorry, speed of electron is given now, and you need to calculate the lambda. So same thing, a de Broglie wave equation, right? Wave particle duality, that equation lambda equals to h by mv. Here it is given to means intermediate U alpha 1 by 137, then the fast Bohr orbit of the hydrogen atom is 331 picometer. These are not required. The required thing is value of alpha 1 by 137 into c. C you know, speed of light 3 into 10 to the power 8 meter per second. Sorry, oh, I have made one mistake somewhere in place. In centimeter I wrote see, I had made a mistake. I was telling you about the units. I myself made a mistake. Why did I write it?
First problem.
Huh? The
Wait,
first
wait,
problem.
first problem.
Yes. Hey, please correct me whenever I make mistake. uh, yes, so it should be 10, right? Yes. Okay. Thank you. Okay, so let us go back. Okay, so the same equation will be followed. Just in case of velocity, it is given that alpha c. You put that and you will be able to solve this. So these are the problems from the Atkins book. Okay, you guys can solve it yourself. I am just giving you the formula and the basic understanding how to do that. Now we are looking at 8.2b. Okay, so the question is calculate the linear momentum of photons of wavelength 350 nanometer. what speed does a hydrogen molecule need to travel to have the same linear momentum? Same formula. Here you need to calculate the P, that is mv, right? So lambda is given, h you know, Planck constant, so you need to get the linear momentum. Now you need to take the hydrogen molecule. What is the atomic mass of a hydrogen? Sorry, here it is the hydrogen molecule, that is H2. So you need to get the mass of the H2, which will be around 2 AMU. Okay, 1.008 into 2, right? So it will be 2.016 AMU. But you need to know that how to go from AMU to gram, right? That is, correct me if I am doing this thing wrong. 1 AMU, I think, is 1.66 into 10 to the power minus 27 kg. Is it correct? Anyone? If I am making any mistakes, please tell me. This is 1 AMU. I think for hydrogen it will be 2.016 AMU. You can convert it to in kg, right? And then do the same thing. You got the M, right? You know the H, and put the thing to get the values. If you are having any problem to understand, please let me know. I'll quickly go through this because there is not much time. From the next time onwards, we will try to solve the questions more rather than discussing the particular the PDF by PDF. I will not go. If you have any particular query, you can always we'll begin with that, but we'll not go PDF by PDF. Okay, just you can ask me your questions and then we'll solve the assignments and this kind of problems, numerical problems. Okay, so the 8.3a, the speed of certain proton is given. What kind of unit is this? This should be millimeter, right? I think they have made some mistake, might have done some mistake, or I am making some mistake. The capital M and small m, what is that? Anyone know? Is it megameter? Something is like that? 10 to the power 6? May possibly. If the uncertainty in its momentum to be reduced to this percent, what is the uncertainty of the location can be tolerated? See, this is a good question. Don't think about the unit right now. I'll tell you what is the so uncertainty. You understand? You need to go back to the Heisenberg uncertainty principle of this position and momentum. Let me write it. So in px, which would be less than h cart by 2, h cart is nothing but h by 2 pi, right? I think you know this. So it is given that delta x is 0.001 percentage. So before going that, so delta px, so your mass is fixed, right? There will be no uncertainty in mass, so there will be uncertainty in speed. Let me write it along the x-axis. We are using only one axis right now, one dimension. So mass, you know, delta x is given, and the limiting value of this is less than equals to this. So for a limiting value case, you can always take v equals to h cut by 2, right? I think I'm making some mistake. Let me go to the wave function thing. I think I'm making some mistake there. Heisenberg uncertainty principle. If I'm making mistake here, I think so. Where is that? Is it less than equals to or greater than equals to? Can anyone confirm?
Sir, greater than.
Greater than, right? Yes. That's why I thought I'm making some mistake here. Yes, it should be greater than. Then only this will make sense, because how else this can have a limiting value. So the limiting value will be, so delta x into m into delta vx will be h cut by 2. This will be the limiting value. So this is what is given here in the question. Is being asked that the speed of certain proton is given, a speed is given, uncertainty in momentum is to be reduced. Acha, momentum is given, uncertainty, so we need to calculate the location uncertainty, the delta p, delta x we need to calculate. So one can also tweak like this. So it is given, and this delta px is given, which is 0.001%, means into 10 to the minus 2, you can write it like this. So this is given, for value of h you know, and then you can calculate the uncertainty in the position. Like this we can solve this question, right? Is it clear? For the second question also, it is given, the certain electron is given, mass of electron you know. If the uncertainty is momentum, same question, same. What is the uncertainty in the location can be tolerated. So that part you can, I think you will be able to solve this question. Now the next set of questions, calculate the energy per photon and the energy per mole of photons for a radiation of these wavelengths. So this is also easy. You know the energy is hc by lambda, right, for one photon. So you put the value of lambda in the denominator, hc by 600 nanometer, right? You can convert it to centimeter, nanometer to centimeter, or meter, to your preference. Okay, and then you can calculate the energy per photon. Now energy per mole of photon will be, you have to multiply that with the Avogadro number, which is 6.023 into 10 to the 23. So that will be the energy per mole of photons. I hope you will able to solve both the questions, right? 8.4a and 8.4b, where the lambda is given, you need to calculate the energy per photon. Please try to do that. I hope you will be able to do that. So the if then I can go to the next question, 8.5a. Calculate the speed of light to which a stationary hydrogen atom will be accelerated if it absorbed one of the photon used in 8.4a. So for hydrogen atom, so you need to calculate what? So calculate the speed, and then again you need to go by the de Broglie's equation, which is h by a lambda is equal to h by p, right? So the photon absorbed is, you know the lambda. I am making some mistake. I am making one mistake. I am making one mistake, I guess. Calculate the speed to which a stationary H atom would be accelerated if it absorbs one of the photons used in the exercise 4. Okay, so suppose it is absorbing 600 nanometer. Okay, 600 nanometer. How much energy will be that? Calculate the speed of which a stationary H atom would be accelerated. Achha, so simple. It will, I think, you need to do the same thing. I think uh, lambda equals to h by p, and again mv. Mass for the hydrogen atom, you know, h you know the wavelength given, so you need to calculate the velocity of the speed. You got it, guys? The 8.5b also tells the same question. Calculate the speed of which a stationary 4 helium, means helium atom for which the mass is given. So this u is nothing but the atomic unit. Okay, so that is amu. you need to convert it to gram or kg. A kg you can convert it by 1.66 into 10 to the power minus 27 kg, I guess, and would be accelerated if it absorbs each of the photons. Same question for B means you just need to do the same thing. Okay.
Sir, please repeat 8.5, yes, sir.
8.5a. So it is said that the calculate the speed to which a stationary H atom would be accelerated if it absorbed each of the photons used in exercise 8.4a. Means these are the wavelengths given. So if it absorbed any of these wavelengths, what will be the speed? Can you tell me how? Means I already discussed, but can you guess how we will try to solve this? So what are the
No,
things you
sir.
have here? So you have lambda here.
Lambda.
Lambda from 8.4 you got your A, B, C, 3 lambdas are given. So it is said that you can use these wavelengths given in this question 8.4a. For 8.5a, for this question you can use these wavelengths.
We can use the formula lambda is equal to h upon mv, right?
Yes, that is the thing. Yes. So you can use that. Why you can use that? Because you have the lambda, you have mass, and you have lambda, you have mass, and you have the Planck constant, so you will get the speed, right? So I think someone asked me this question. He got it right.
Yes, sir.
Yes or no?
Yes, sir. I got it.
Yes. Okay, thank you. So you will be able to solve both the questions, right? 8.5 and 8.5b. It is the same question. In case of hydrogen atom, now helium atom is given and the mass is also given. You need to convert it into kg. Okay. So let us go to the next question. Okay. So this is interesting. Glow-worm of mass 5.5 grams emits red light, which is 650 nanometer, with a power of 0.10 watt, entirely in the backward direction. To what speed it will have accelerated after 10 years if released into a free space and assumed to live? So I know a lot of information is there, right? So let us take what things are there. One mass is given, one lambda is given. Okay, so we know somewhere that we need to use the de Broglie wave equation. Okay, mass is given, lambda is given, and what else is given? That this worm can means emit a red light with a power of 0.10 watt. What does power mean? Power means energy per. So here comes another time I told you the conversion between the units. What does watt mean? 1 watt. The work done can be done in 1 second, right? Suppose 1 watt is 1 joule per second, right? So this is actually a rate of energy emission, or rate of energy you can say. Yes, a rate of how much is it giving or radiating energy per second. So so it is given that what will be the speed it will have accelerated after 10 years. So time is also given 10 years. So let me give you the information what we have from here. We have, so got the question right. Don't suppose one object is there which has a mass of 5 gram. Okay, and it is emitting red light of 650 nanometer. So lambda is given. Okay, now what else is given? That the radiation power, that is suppose power or P is how much? 0.15 watt, something like that. Just let me check it once. It is 0.10. Oh, let us not bother. 0.10 watt. That does mean 0.10 joule per second, joule second inverse. Okay, so this much power it is emitting, and it is being said that if it is kept for 10 years, so suppose it is emitting power at backward and it is moving forward. Okay, so it has some linear momentum, right? So you know the momentum formula is that lambda equals to h by mv. Okay, so lambda is given, m is given, v we don't know what speed it will accelerate, h by m lambda. So for one so this will be for one photon. Okay, and it is radiating 0.10 joule per second for 10 years. It will emit 10 years, 10 into 365 days into 24 hours and 3600 seconds. You got my point what I am trying to write here? So I will not solve this because I need a calculator or something like that, but you understand this much power or this much energy. I think I am writing in a very bad manner, right? It is going upward. Energy emitted in 10 years. So this will be equivalent to this. Okay, these many joules. Suppose this is coming as this many energy E. So how many photons are inside? Means how many photons are there? So the number of photons will be E by H nu, or again E by Hc by lambda. So let me write it E total, then it will make sense. E total. Huh? Is it making sense what I am saying? Anyone can reply please. If anyone having doubt, I'll say again what I am trying to convey you. Please anyone reply if you are getting it. Anyone? Please. A positive response will also work. I can't hear you, please. Okay, so what we are trying to get that at 10 years, how much energy this will emit. Okay, and if so this so E total is the total energy emitted in 10 years. Now how many photons are there? So that is E total by h nu. One photon, one photon we know it is h nu or hc by lambda, right? So it will be something like that. So these many, so number of photons emitted is Et. I am rewriting this hc by lambda. So if these many number of photon have been emitted, then the next question is okay. Eventually I forgot the question. Let me check. What is the velocity, right? The question is a glowworm of mass m emits at this entirely backward. What will be the speed? What speed will it have accelerated after 10 years into the free space and assumed to live? Means this many photon it has released. So the momentum will be multiply of that. For one photon, so what I am trying to say, so So these are the number of photon it has emitted. So for one photon, the speed would be, so for one photon, the speed would have been v by h by m lambda for one photon. Now for n number of photons, the speed will be this n multiplied by h by m lambda. You got my point? So n is E total by hc by lambda into h by m lambda. So let us cut a few things. I guess we can h cut and lambda will be gone. So what is left? E total by c into m. So mass of that thing 5 gram that is given. The total energy you need to calculate, and that is the speed of light. So this much. So let us see if it matches with the dimension. So energy will be joule, right? I think I have made some mistake, right? It is meter per second and mass will be in kg. So what does joule is? Joule is energy. Energy is force. Joule is Newton meter, right? Force into displacement. You guys getting right what I am trying to do? And Newton is force. Force is mass into acceleration. That is kg. Well, that is how I remember the units. Newton is kg. Newton is force. Force is from Newton's law. It is mass into acceleration. That is kg into meter into second inverse second square minus 2. This is Newton and this is meter, so meter square. So this is that joule. So it is kg meter square second minus 2 divided by meter second inverse into kg. So kg cut, meter will 1, second inverse will, here it will go 1. So actually you are dimensionally you are getting meter per second, which is unit of velocity. You got my point what I was trying to discuss? Here I was just checking if I am getting the unit or the dimension for the velocity itself. And that is how you can always cross check. First we have to get the total number of energy emitted in 10 years. Now we have to see how many photons are emitted. So number of energy by number of each photon. So that is n. So this is n, right? Now one photon, if one photon is emitted, then your velocity is h by m lambda. Now in 10 years, n number of photons has emitted. So your velocity will be n into h by m lambda. That is how you are getting this expression. Et by c into m. M is mass, c is the velocity of light, Et is the total energy. And that is how I showed you that it is dimensionally you are also getting the velocity. Any doubt in this question? Anyone? Let me check the chat box. Share the question. Yeah, sure. Acha, this was okay. Yeah, you can use Mathematica or GraphPad. Yeah. You can use any one of those. How to get the PDF of this lecture? So I will share the notes. I will share the notes and I will include the questions that has been discussed, all the things I'll share, and the links will be given. Links will be given to you.
Also, the PDF of the lecture that Dr. Datta takes.
Yeah, I think it is already given to you. I guess so. Let me show you. My screen is visible, so the way I am seeing my portal right now, you won't be seeing yourself, because as I am shared all the things together, you can see I have been given week 1, week 2, all the things are here. I think currently you can see only week 1, week 2, and week 0.
Yes, so only week 1 and week 2 now.
Yes. So that is something privilege has been given to me, but that's not a problem. So you can see the study. Can you see study material? Something are you being shared? Something like this? Study
No,
material?
no.
Okay, that is not yet being circulated, or will be circulated later. So that, so I can't really help you with. I'll check with the NPTEL guys, NPTEL whoever is authority is there. I will check with them, and we'll come back to you. If we can share those study materials with you. Okay. I thought it was already shared with you.
No,
Because
we have an option called download videos, but we don't have a PDF material.
okay. So actually, the two things I have been shared these things, and this link is already there with me. And another thing is that my supervisor is Datta sir, so I am getting the PDFs and presentations from him directly. So I'll ask the NPTEL authority if we can share that with you. If they said yes, I'll share them the same link. So we have to share some Drive link with you, these recordings, these assignment problem solutions, these discussion videos, even these notes will also be there. So we'll discuss that. Okay. Okay. So I'll also share these questions what we are discussing today, and I hope we can solve 2 or 3 more questions. But I don't think we'll able to solve all the exercises problem. But this question is very interesting, right? It's 8.6a. Did you understand this?
Understood, sir.
Anyone? Priyanka, Shatya, um, um, Mr. or Miss Pandey, Achishman, anyone? Kastav, the last question, did you get it? This 8.6a, that a mass of 5 gram emits red light with a power of this much, and at the backward direction, so that's why it will speed up in the forward direction. So to what speed will it have accelerated after 10 years if released into a free space? So there is no friction, so those things are not coming into play. I hope you got this. No one is responding, so I am assuming you got this. The same question, I think. So instead of 8.6a, we should have discussed 8.6b, because it is much more clear here, because it has written a photon powered spacecraft instead of GLOWON. So the questions are mostly given to means what to confuse you, but you need to play with the whatever data is given. So the same question, your mass is given, lambda is given, your power is given. Now what speed will it have accelerated after 10 years release into free space? Please try to solve these questions yourself. Then 8.7, that question, that a sodium lamp emits yellow light, so lambda is again given. So how many photon does it emit in each second if its power is 1 watt? So 1 watt means 1 joule per 1 second. So in 1 second it will emit 1 joule of power. So so how many photons are there in 1 joule? 1 joule by 1 joule by hc by lambda. So lambda is given 550. Same you have to do for 100 watt. 100 watt power means 100 joule per second. So 100 joule by hc by lambda. So you will get this, how many photons will be emitted. Same concept as 8.6a and 8.6b. Then the next question is 8.7b. Same question, that lambda is given, power is given, you need to calculate how many photons you can get. All of you will be able to solve this question, right? At least these 7 or 14 questions, 8.6a to 8.7. Should I
Yes,
discuss? Yes. Okay. Thanks for your response. Should I? Where is the face? Where I went to very far. Oh my God. Let me get back to the 274. So you have this kind of this Atkins book. Do you have, or at least the do you have this Atkins book, physical chemistry Atkins book?
yes, sir. I'm having a soft copy.
Yes. Yeah, you are having it. Yeah, good. So please try to solve these questions at the back, and also if you face some problems regarding solving this question, please come back and we'll discuss. Please try to solve the this part and the numerical part also. So these are some exercises, some numerical problems, some theoretical problem is also there. We'll not go deep into the black body temperature and Owen's law. We'll not go there, because eventually we are from this class we'll go to the more sophisticated one dimension 1D box, 3D box. Why I am solving these problems? Because the importance is, again, see, I myself had made some mistakes in you saw, right, that I have made some mistake in units or even in the formula. So you have to grasp that thing well, means you have to, before beginning of this physical chemistry course, you need to clear those unit and the whatever the relationship between the units are there, you need to be very sure about that before starting. So these numerical problems will actually help you to solve the rest of the problems which will come in the next round. Okay. So should we discuss some more, or because the time is already up, so if you want to dissolve, then we can dissolve, or we can means carry forward this question next time also. So what do you suggest? Anyone? Is it interesting or just boring? You have to give me some response, because then I will try to ready the next lecture accordingly, because I understand myself that discussing the what sir has already taught, so that will that is not good, because that will kill time also. You have already seen the videos, so that will waste your time also. So what do you think? Means please, anyone can give me suggestions, please, what to do from the next week onwards.
So maybe you can give a problem and give us 5 minutes to solve it. And once we solve it, then we can discuss it.
Sure, sure, sure. So for now, suppose, see, we could not solve this 8.8 to some more questions, right?
We can try to solve it at home and then discuss
Yes,
next.
yes. So please try to solve at least 8 point. So these questions you try to solve. Let me zoom out a little bit. I know you can't. You'll not be able to see the exact questions. So please try to solve from 8.8a to at least these many questions. Whatever numerical problems, if you are also trying, if you have time, please try to solve. Okay. So that would be good, and then we'll discuss, and it will be beneficial. Any more suggestion, Priyanka?
No, sir. That's it.
Okay. And others, please. Should we discuss the means whatever means the lecture notes again, or means whatever, what suggestion do you have regarding that? Should we discuss those things in between every lecture, or I should just discuss the important formulas and then go ahead with the class, right? That would be good, because the formula, what formula we'll use, that will be required, so we can do that. So as this is the first class, so I'm trying to understand what can we do for the next weeks. So okay, so let us actually stop the recording here. I will stop the recording here, and